So, look at this problem. We have two generators, identical generators connected in parallel to the common bus bar of this way. The sequence reactances of the generators are given. X1 equals to X2 0.2 per unit, X0 equals to 0.05 per unit. The neutral of the one of the generator is grounded by a reactance of 0.05 per unit and the other generator is isolated from the ground. So, let me assume that the first generator neutral is grounded with a reactor of Xn, second generator neutral is ungrounded, where that neutral reactance value was 0.05 per unit. Second generator is ungrounded as he is saying. Now, a most common short circuit fault taking place on the common bus bar with a fault reactance of 0.5 per unit. What do you mean by most common fault here? That will be generally of LG fault we are going to treat now. So, we have a most common fault means LG fault at the terminals of the alternator, terminals of the bus bar, common bus bar. Maybe here we have a line to ground fault occurred, and he is saying that the fault reactance is equals to 0.05 per unit. This was the data he is providing, and the question is now the voltage of the zero sequence network in terms of kilovolts when the operating voltage of the bus bar is 13.2 kV. So, first of all, let me solve this problem completely in the per unit quantity. Then we will convert that per unit zero sequence voltage number into kilovolts by using the 13.2 kV what he is giving as by treating that as a base. Well, as he is saying line to ground fault, we know that in the LG fault, three sequence networks will be connected in parallel. Positive sequence network, negative sequence network and zero sequence network will be connected in parallel. For example, if you check the positive sequence network of this one, the positive sequence network will be looking of this way. This was for the first generator, positive sequence network up to neutral, second generator, positive sequence network up to neutral. Let me keep this like positive sequence network. Well, and this is a location of the fault, that means this one is a location of the fault, and this impedance, positive sequence impedance J.2, this impedance also J.2, and you can check now the positive sequence equivalent impedance with respect to the location of the F is J0.2 in parallel with J0.2 means it is J0.1 per unit by shorting the sources. J0.2 parallel with J0.2 turns to be J0.1 per unit. Well, and he is not mentioning anything regarding the pre-fault voltage. Of course, he said 13.2 kV here. We will assume that voltage to be 1 per unit now. That means positive sequence Thevenin voltage equals to 1 per unit we are going to assume, and the system is assumed to be balanced before occurrence of the fault, means we have only positive sequence Thevenin's voltage existing before the occurrence of fault, right. Next, similarly, if you look at the negative sequence network construction on the same way, this is the negative sequence impedance of generator 1 and we do not have any source here, and this was a negative sequence impedance of generator 2 and we do not have any source here, and this was a neutral, and you can see now Z2 equivalent value, Thevenin equivalent impedance with respect to the location of the fault, this also comes like J0.1 per unit, and we do not have any Thevenin voltage here, V Thevenin 2 is equals to 0. That is the thing. That was the negative sequence circuit. Next, if you look at the zero sequence network now, zero sequence network, this was a crucial thing what you have to observe majorly, because one of the alternator was neutral grounded, the other alternator was isolated from the ground. So, zero sequence network generally constructed with respect to ground up to neutral. For the first generator we are keeping J0.05 zero sequence reactance of the generator. From neutral to ground we should keep 3 times of the Xn whatever we have here, means I should keep this number like J0.15 this was for the first generator, whereas the second generator was neutral ungrounded, means up to neutral we should keep J0.05 and neutral to ground we do not have any impedance to be placed, means infinite impedance we have to keep. And then if you measure zero sequence Thevenin impedance with respect to the location of the fault, means Z0 equivalent with respect to location of the fault. If you see that this is J0.15 in series with J0.05, that turns to be J0.2 per unit, that was Z0 equivalent. So after knowing these positive sequence impedance, negative sequence impedance as well as zero sequence impedance values, now we will construct the Thevenin equivalent circuit. Thevenin equivalent circuit in the sense positive sequence Thevenin equivalent circuit, negative sequence Thevenin equivalent circuit, zero sequence Thevenin equivalent circuit, and for the LG fault all the three are connected in series. Like this we can see Z1 equivalent with a voltage of V Thevenin 1 per unit of course, this is a positive sequence circuit, and Z2 equivalent up to neutral, no voltage source as I said you earlier, zero sequence circuit up to ground, Z0 equivalent, no voltage source, and these are the voltages now like plus minus VR1, plus minus VR2, plus minus VR0. Of course, this was our requirement, VR0 value we have to find, and the three networks are connected in series of this way, and across to this one we should keep 3 times of the ZF. That ZF is mentioned in the problem like J0.05, J0.05 means this number is J0.15. Now simply find out the current circulating in this loop, that current multiplied with Z0 equivalent will give the value of VR0. Let me keep these numbers, this is J.1, this is also J.1, it was J0.2. So that we can get now the current circulating, or we can say simply current flow in this zero sequence circuit, IR0 in our notation, IR0 is equals to only one voltage source you have, so called V Thevenin 1 by Z1 plus Z2 equivalent plus Z0 equivalent plus 3 ZF you have. It turns to be 1 per unit by J.1 plus J.1 plus J.2 plus J.15, means this number is 1 by J.4 and then J.55 will get approximately like 1.82 at an angle of minus 90 degree in per unit form, 1.82 at an angle of minus 90 degree in per unit form. Now VR0 equals to, this what our requirement in the problem, zero sequence voltage equals to IR0 into J0.1 with minus IR0 into Z0 equivalent, means you can get like minus of 1.82 at an angle minus 90 degree into Z0 equivalent is J0.2, and product will give you 0.364 per unit, and I have concentrated only on the magnitude of this, mod VR0 equals to 0.364 per unit, and if you are converting this one into kilovolt, that number we have to multiply with the base voltage given in the data, so that VR0 in terms of kilovolts I am writing here, it was 0.364 per unit. Base voltage means we should multiply with the kV base per phase, which is 13.2 by root 3 kilovolt. So the answer comes around 2.77 kilovolts. Thank you.